Hello, students, and a very warm welcome to all of you. I hope you are ready for a revision of one of the most important chapters in your physics syllabus. Today, we're going to completely revise force and the laws of motion. We will break down everything you need to know, right from the basics to all the key concepts for your exams. So, let's get started.
Okay, let's start with the simple question, something we've all experienced, haven't we? You're standing in a bus, holding on, and suddenly it lurches forward. What happens? You feel like you're thrown backwards, right? Why does that happen? Well, this very common feeling holds the key to understanding our first big concept.
So before we can understand why things move or why they stop moving, we need to talk about the cause. And that cause in the world of physics has a special name. It's called force. So let's ask, what exactly is a force?
In the simplest words, a force is just a push or a pull. Just think about it for a second. When you kick a football, you are applying a force. When you pull open a drawer, that's also a force. It's basically any effort we apply that can change an object's state of rest, its motion, or even its shape.
So what are the effects of a force? What can it actually do? Well, it's quite powerful. A force can make an object that is standing still start to move. It can stop a moving object. It can make a moving object go faster or slower. It can change its direction. And it can even change the shape of an object, like when you squeeze a sponge or a rubber ball.
Now, this is a very interesting idea, the difference between balanced and unbalanced forces. Imagine a game of tug-of-war. If both teams are pulling with the exact same strength, the rope doesn't move, right? Those are balanced forces. The net force is zero. But the moment one team pulls just a little bit harder, the forces become unbalanced. There is now a net force and the rope starts to move. So, the most crucial point to remember is this: only an unbalanced force can change an object's state of motion.
This whole idea about changing an object's state of motion, it leads us directly to the brilliant work of Sir Isaac Newton and his very first law of motion. This is famously known as the law of inertia.
Now, the law is stated very precisely. It says that an object at rest will stay at rest, and an object that is moving will keep on moving with the same speed and in the same direction. It will only change its state if some external, unbalanced force acts on it. In simple words, objects have a natural tendency to just keep doing what they're already doing.
And this natural tendency of an object to resist any change in its state of motion, that property is called inertia. Now, let's go back to our bus example. When the bus suddenly starts, your feet, which are in contact with the bus floor, move forward. But the upper part of your body, because of its inertia, wants to remain at rest. That is why you feel that jerk backwards. It's the very same reason we must wear seatbelts in a car, to protect us from our own inertia if the car stops suddenly.
Here is a perfect classroom demonstration of inertia of rest. Think about a game of carom. When you stack the coins and hit the bottommost coin with the striker, what happens? Only that one coin shoots out. The rest of the stack, because of its inertia, wants to stay at rest, so it just falls straight down. A beautiful example.
So, an important question. Do all objects have the same inertia? The answer is no. Inertia depends directly on the mass of the object. The more mass an object has, the more inertia it has. This means it is harder to change its state of motion. It is much, much easier to push a bicycle than to push a train, isn't it? That's because the train has much more mass and therefore much more inertia.
Okay, so now we understand that a force is needed to change motion. The first law told us that a force is needed. Now the second law, this is where we get into the calculations. It tells us exactly how much force is needed. It gives us a mathematical relationship between force, mass, and acceleration.
But before we can fully understand the second law, we need to learn a new term, momentum. Momentum is simply the product of an object's mass and its velocity. You can think of it as the quantity of motion that an object possesses. A heavy truck has more momentum than a light car moving at the same speed. And because velocity has a direction, momentum also has a direction.
This is how Newton originally stated his second law. It sounds a little complex, but it simply means that the force you apply is related to how quickly you are trying to change the object's momentum. A bigger force will cause a much faster change in momentum.
Now that whole big statement simplifies into one of the most famous equations in all of physics. F equals m into a. Force equals mass times acceleration. The SI unit of force is the Newton, which we write as N. So what is 1 Newton? It is the force needed to give a 1 kilogram mass an acceleration of 1 meter per second squared. For example, if a 10 Newton force acts on a 2 kilogram body, what will be the acceleration? Well, acceleration will be force divided by mass, so 10 divided by 2, which gives us 5 meters per second squared. It's a very simple and powerful formula.
And here is a fantastic real-world application of this law. Why does a cricket fielder pull his hands back when catching a fast ball? Think about it. By pulling his hands back, he is increasing the time it takes for the ball's momentum to become zero. And since force is the rate of change of momentum, if you increase the time, you reduce the rate of change, and that reduces the force of impact on his hands, which of course prevents injury.
And now we come to the third and final law of motion. This law tells us something very, very profound. It tells us that forces never exist alone. They always, always come in pairs.
The law itself is so simple and elegant. To every action, there is an equal and opposite reaction. It's easy to remember, but the meaning behind it is incredibly important. And sometimes it can be a little bit confusing. So, this is the most crucial point, and Beta, please remember this for your exams. The action and the reaction forces always act on two different objects. They are equal in size and opposite in direction, yes, but because they act on different bodies, they do not cancel each other out. This is a very common point of confusion, so please be clear on this. Let's look at a couple of clear examples. When a gun is fired, the gun pushes the bullet forward. That is the action. In return, the bullet pushes the gun backward with an equal force. That is the reaction, which we feel as the recoil. Or think about just walking. Your foot pushes the ground backward. That is the action. The ground, in turn, pushes your foot forward. That is the reaction. And that is the force that actually moves you forward.
All right, we have covered all three of Newton's laws. Now, let's just quickly put everything together and go over some very important tips that will help you to score well in your exams.
This table is a perfect snapshot of what we've just discussed. Remember, the first law is all about the key concept of inertia. The second law gives us that very powerful formula F equals ma. And the third law is about action-reaction pairs. This is a great slide to take a screenshot of for your quick revision.
And finally, some very crucial reminders for your exam. Beta, please do not forget to write the correct SI units in your answers. Marks can be cut for this. Always remember that momentum is a vector quantity, which means it has a direction. F equals ma is used to calculate the net, or the resultant, force. And, as we just discussed, action and reaction forces act on different bodies. Most importantly, practice numerical problems. That is the absolute best way to master these concepts.
And with that, we conclude our revision for this chapter. I really hope this session has helped to clarify all your concepts. Physics is happening all around us, every single moment. So my final question to you is, as you go about your day today, just look around you and think, which of Newton's laws do you notice the most? Keep learning, keep questioning, and all the very best for your exams.